Thanks, Greg. Thank you to the organizers for inviting me to give this talk. It's my first time, incidentally, at the Newton Institute, and I've had a pretty intense and good week so far, so I'm pretty happy about that. It's quite a perfect time slot to talk about something dry, given that we've all come back from Robinson College and we had to face that storm outside. The work I'm going to be talking about has been started by Lucas Göring from Nottingham Trent a good decade ago. He's been joined by Jana Lasser, who did her PhD with him and is now in Aachen. And most of the recent developments were carried out by my PhD student, Matthew Threadgold at the University of Leeds, and it's in collaboration with Steve Tobias sitting in the back row. So to start with, I'm imagining that most of you have seen this picture somewhere. So it's taken from the movie Star Wars: The Last Jedi, and it shows a landscape typical of planet Crate, where it's an imaginary planet, for those of you who haven't watched the movie, which is pretty attractive in the sense that it's tiled by these polygons. It's a very recognizable thing. And maybe some of you might have thought that this is coming out of the imagination of the sci-fi writers, but it turns out it wasn't. In this picture, not everything was CGI'd. They went, in fact, on location at Salar de Uyuni in Bolivia to film these scenes, and you can see a magnificent landscape that we can observe at Salar de Uyuni. So this is taken from a paper in JSTOR, and as you can imagine, this is quite attractive for tourists. And has been used for travel agencies, particularly here. I found this picture on the website of Travel in USA, showing a picture of Badwater Basin, which is located in Death Valley, showing, again, some magnificent polygons here. So what we're talking about are dry salt lakes, but before explaining what these dry salt lakes are, let me just tell you what salt lakes are. They're lakes that are located in terminal valleys, which means that water comes in by various means. That can be rainfall, that can be groundwater flow, which is a major component, and it accumulates in what we identify as a lake, right? Since it's a terminal valley, there's only one way water can exit the system, and it's through evaporation. So as you can imagine, when water comes in, it drags with it all sorts of minerals and nutrients, and these get effectively deposited inside the lake, making it a salt lake, ultimately, when water evaporates. Now, what happens if the evaporation rate is larger than the rate at which water is brought into the system? Is that, imagine that you have a water surface of the lake here, that water surface goes down, and it can eventually entirely dry out the visible part of the lake by going below what we would imagine is the bottom, the ground, the ground of the lake. But in fact, the system is not empty of water. What happens is that the water table typically can be found about tens of centimeters below the surface, or the ground, depending on how you want to see it. So there is water in the system, and as you can imagine, this water is salty, there's a lot of mineral that come in, and as it evaporates, goes up like this, water gets out of the system, but the minerals stay in and tend to precipitate to form a crust at the surface. This is the phenomenon that we're witnessing. Some more pictures taken from one of our papers here. So this is a picture taken by a professional photographer, Sarah Marino, of this, I believe, is Middle Basin in Death Valley. This is Owens Lake near Los Angeles, and this is Badwater Basin in Death Valley as well. What I'd like to draw your attention to here is the size of these polygons. Across all these different regions in the world, we've managed to identify that there's this length scale that seems to be the same. And it is that these polygons are roughly 1 to 2 meters across, and we typically see ridges that are about 10 centimeters tall. Now, it's quite tempting to try and explain the formation of these structures using solid mechanics, because we don't see any fluids here. And particularly looking at the stresses on the crust, theories like cracking or wrinkling have been looked at, but they tend to predict a wavelength for the pattern that would be proportional to the crust thickness. Well, it turns out that Lucas Göring, our co-worker here, has traveled extensively and has seen these lakes all around the world. He's noticed that there's a huge variability in the crust thickness. These ones typically have a crust thickness of roughly tens of centimeters. And you can see a very nicely formed crust, quite thick, from the ridges. but he's also seen them on the Skeleton Coast in Namibia, where if you were to set your foot on the crust, you would actually break it. And in spite of that, the polygons are still roughly of the same size. So we need to look at something else. The solid mechanics here doesn't explain this phenomenon, and so we decided to have a look at the groundwater flow that is taking place below the ground level, below the visible area of the lake. So this is going to be our model. We're going to be looking at an incompressible flow inside the porous medium, and of particular attention, we're going to be paying particular attention to the dynamics of salinity. So these are our equations. So we all know the incompressibility condition. This is going to be an advection diffusion equation for the salinity. And instead of the Navier-Stokes equation, which we generally have in a continuous medium, we're going to take this law, which is the Darcy law. It's effectively the equivalent of the Navier-Stokes equation. It's the macroscopic conservation of momentum law in a porous medium. And like for the Navier-Stokes equation, when you do convection problems, you can add a buoyancy force term on the right, which is going to be proportional to the Rayleigh number if you design your parameter, if you choose your parameter wisely. So this is what we have, and the flow is going to be forced by the imposition of the boundary conditions. We're going to have a pure fluid, or purer fluid, at the bottom of the lake. We're going to have a saturated fluid at the surface to model the influence of the crust that we have here, salt crust. And we're also going to model evaporation by imposing a constant through flow here at the upper boundary. So really what we're looking at here in this system is an incompressible flow in a porous medium. And in this flow, we're looking at the competition between two different phenomena: the through flow that's going upwards, that entrains the fluid upwards due to evaporation, and the buoyancy flow here that wants to make the fluid go down due to the presence of a crust at its top. Yeah.
Did you mention anything about the porosity of the medium?
It's hidden in the Rayleigh number.
Okay, but
yeah.
In the actual field,
yeah.
Is it homogeneous?
There is some variability. That's something we might want to look at some point, yes. There are some parametric variability that we haven't taken into account yet. Yeah, that's a good question.
Sorry, what's the velocity boundary condition at the bottom?
You don't need one because it's a first order equation for the gradient of pressure. I can talk about that later.
But the water has to come into...
Yeah, so what we do is we impose, there's two ways to impose it. So you impose it through the, you don't solve actually an equation for the velocity. It's just left-hand side velocity equals. So you're solving a Poisson equation for the pressure. And for the bottom boundary condition, what we're imposing is, we're imposing a constant average, which is equal to the average at the top, and then we're resetting it. I mean, I can talk to you about it after. Okay, so that's the system. Oh, and the competition between these two phenomena that I was talking about is conveniently represented inside the Rayleigh number as being the ratio between buoyancy and evaporation. So if we let the crust diffuse initially, so if we set the salinity to be 0 everywhere, we're going to be surfing along the stable manifold of a base state, which is an exponential distribution of the salinity in the domain. And here I've introduced the finite size of the lake, h. That's going to be a numerical parameter that we're going to have. But essentially we end up with this base state, invariably. We end up going along this. And so it's interesting here at this point to look at the stability, the linear stability of the state, to see whether we're going to trigger convection or not. So we perturb it in the usual way, small perturbation of wave number in the horizontal direction k and growth rate sigma. And we obtain here the marginal stability curves. So sigma equals 0 for various lake depths. So h equals 2 is this blue curve, then 3, 4, 5, etc. What we can see here is very quickly we reach an asymptote, which is the infinitely deep lake limit, where we can extract the critical value of the parameters. We have a critical Rayleigh number of 14.35 and a wave number roughly of 0.76. Okay? On top of this figure, we've overlaid the fastest growing eigenmode, so in dashed line. So that's the mode that we're generally going to be observing if we run a numerical simulation at a certain value of the Rayleigh number. Particularly for Rayleigh equals 100, this is what it looks like. Pay attention to the fact that this is a logarithmic scale. So really what we're looking at is an instability here of the solidal boundary layer, where this function is order 1. Okay? All right, so if I take this flow in 2 dimensions on this relatively large lake here, and I let it evolve, this is what happens. So first of all, we've got the exponential distribution of salinity. We're always going to be converging to this. And then the instability sets itself up, where we've got the formation of rolls, and these rolls become more and more elongated, producing salt fingers in a way here. We have salinity plumes that are descending, and they're intertwined with upward flow of purer fluid. In our problem, what is interesting to do is to actually try to relate this to the pattern at the surface of the dry salt lakes. And we can do this by looking at the flux of salinity into the surface. This is this quantity Jz that I've written there. It's got an advective component, which is the velocity times the salinity. And due to the boundary condition, this is always 1, okay? And the second component, which is a diffusive component that goes like the gradient of the salinity, vertical gradient of salinity. And due to the orientation of the axis, in our case, it is preceded by a plus sign, but that quantity is always negative. So it competes against the advective flux. So we can look at this against a random snapshot in our simulation. This is one snapshot that we had, and Jz is plotted there. So we can clearly see that there's a correlation between the plumes and positive salinity flux into the surface. What is happening is because the plumes do not present any gradient or very small vertical gradient of salinity, the salinity flux to the surface is dominated by the advective component, and we're essentially injecting salinity into the surface. Conversely, if we place ourselves above an upwelling, that upwelling compresses the solidal boundary layer, and we are creating a large gradient of salinity, which overcompensate for the advective component, and we end up stripping the surface from salinity. So this is what we have, this is the phenomenology that we get here. Now this is somehow counterintuitive. Velocity goes down here and we're injecting salinity, so it's always good to see what happens in the field to see if really this is good or not. So Jana Lassa went to Owens Lake in California to make some measurements of the salt concentration in the fluid below the salt polygons. So she went out and she dug trenches where the polygons were. And you can see here, she's carefully located the salt bridges of the polygons, and these correspond to the data she obtained at 2 different sites, okay? What you can see there by looking at the salt concentration is that there are pockets. Here, for instance, this is another one. Here, it's a bit harder to see with a contrast on the screen, but I can see one on my screen here. And there's another one here. There are pockets of higher salt concentration located immediately below the salt bridges. And this is, in a way, a confirmation, or it goes in the same direction as what we observe numerically with this phenomenon of injection of salinity above the downwellings, okay? Now I'm going to be showing you a 3-dimensional movie of the instability so you can see how it forms and then how the pattern evolves at the surface. What I'm going to be showing you is a Rayleigh of 100 and a depth of lake of 10, and this is a relatively large domain size, 24 pi by 24 pi. The side faces represent salinity, and the top face represents the salinity flux into the surface. So what we have here is that red, we're injecting salinity into the surface, and blue, we're essentially sending it back into the lake. So I'm going to be showing you this. Where do I have it? Okay, there we go. So what you can see immediately is the formation of small-scale structures while the plumes develop. And if you pay attention to the structures, they're going to become larger and larger through some merging events and slow morphing of the edges of the polygons that comprise it. But also something interesting that we notice is that there seems to be macrostructure that evolve very slowly. And inside these macrostructures, we see some smaller structures, which we call protoplumes or protoribs, which tend to move faster and eventually end up crashing at one end of the polygon. So there's this sort of time separation that is also at play here. Okay. Back to the presentation. So to summarize from the pattern formation perspective, what we've observed here, so we had these small patterns and they became larger. We tried to characterize that using a representative value of the wave number. In particular, what we decided to do is to look at the barycentric, what we call the barycentric average of the power spectrum. So you take the salinity flux of the at the surface, this function here, you Fourier transform it, and then you make a barycentric average of it. Okay? So it's going to take into account all the modes. And so the visible pattern that you see has a certain size, but the number that you're going to get out of this algorithm is going to underestimate it, because we're also taking into account smaller contribution of these small wavelength modes. Okay, so we're underestimating what we're looking at. And when we look at this quantity, we can see that along the simulation, it goes down, the pattern size increases, and this is for 3 different simulations, and it tends to a value that looks statistically constant at long enough times. So what we see there is that this value seems to be the same for all the simulations that we ran, and if we turn this back into dimensional quantities using, say, the data from Owen's Lake for the non-dimensional constants, we obtain a value that is roughly 1 meter. If I remember well, it's more 1.2 meters, just rounded down. So this, bear in mind that this underestimates the size of the visible polygons here, okay? We have also available some field data provided to us by Joanna Neild from the University of Southampton. So she's an expert in terrestrial laser scanning, and she's provided quite a number of these pictures to us. So this is on the left from Badwater Basin, and this is from Owen's Lake. Clearly, you can see that the pattern size, as I was claiming in the beginning, is roughly 2 meters across, okay? And this ties in very well with the numerical observations that we made, which is that 1.2 meter, roughly, is underestimating the size of the polygons. So that ties in pretty nicely. One thing that I mentioned is plumes. The plume typically look like elongated plumes or salt fingers. And if you look at the field data from Jana, well, they don't really look like this, do they? They tend to be looking like a sort of aspect ratio 1 pocket, right? So there's a drastic difference there, and that got us worried at some point, but we decided to ditch the usual 2-dimensional representation and look at the 3-dimensional representation of these plumes. So that's what we did there, and what you see is an isocontour of the salinity. This is S equals 0.75, if you're curious. So we're 3/4 of the way to saturation, and I flipped the plot so that the higher this goes, the more the plumes penetrate deep into the lake, right? So that we can see something. So pay attention to this polygon. This is a mature polygon. This is a late time. On this mature polygon, you can clearly see that there are 2 types of points. There are the points located on the edge of the polygon, which are associated with what I would call a salinity sheet. Now that salinity sheet doesn't penetrate really deeply into the lake. In fact, if you look at it here, it's kind of an aspect ratio 1 disturbance of the flat surface there. There's another type of point that you find. It's obviously the nodes, and below the nodes of the polygons, what you see typically are plumes that penetrate far deeper into the lake. Okay, so there's these 2 types of points. So we went back to Jana and we asked her, where did you actually dug your trenches to make these measurements? And she told us that she was very careful to cut in the middle of opposite edges of the polygon. So what she's witnessed here is in fact the trace of these salinity sheets and not the plumes, okay? We can do the same thing numerically. We can just take a random cut across the system and look at what the salinity looks like, and hopefully, yeah, I think you can see it. Okay. So hopefully that's quite clear that this 3-dimensional cut of this cut of the 3-dimensional system is drastically different than this 2-dimensional simulation. You should see that the salinity here looks more blurry. There's less strong variation. The definition of the plume is less strong than in this plot. And in particular, what you should be able to notice is the presence here of structures that seemingly have an aspect ratio close to 1. And so, yeah.
Maybe, what's that horizontal black line in the Jana data?
This?
Yes, what's that?
Oh, that's the separation between the top and the bottom. Sorry, there are two field sides.
Okay. I wondered when you were going to talk about that.
No.
Obvious stripe.
So this is one side, and this is another side.
All right. Well, let me suggest that you separate those pictures,
I will do that.
or at least draw a line.
A more visible line. Yeah. Okay. Thank you. So yeah, what we can see here is the presence of these structures here, which are quite reminiscent of the structures that Jana observed in the field. Okay. So that comforts us. There is a couple of things that I want to say. Am I running out of time?
Yeah.
Okay, I'll be quick. So what we have here is essentially looking at the parametric dependence. There's one parameter in our system, which is the Rayleigh number. So what we're looking at is the wave number during the simulation that it evolves. And we see that at small times, we're close to the fastest growing eigenmode, as expected. And as time goes, we're going toward these data points. These are not finished simulations. We want to go further. It's not entirely settled yet. So it's still going to the left, but it's interesting to compare that with site data. So the black triangles are Owen's Lake. The blue triangles are from Badwater Basin. I've already spoken about these lakes. And the yellow triangles here are taken from Suapan in Botswana. So there's another continent and similar types of length scale. Okay, so I'll leave you with this. This is the material that we've written on this. Hopefully I've introduced a problem that I find quite interesting. Hope that you're also fascinated by this problem. And hopefully we've made a link between the patterns that we see at the surface of these dry lakes and actually the fluid dynamics that is taking place below it. Thank you.
Okay, so maybe time for just one or two quick ones first.
In the real system, you probably also have a temperature gradient, right?
Yeah.
Which you discarded. And if you were to put it, would you be susceptible to double diffusive instability? Because that would...
So we looked at actually the coefficient of expansion is about 1/200th of the one of salinity. We looked at that. And so it would be a far from dominant contribution. Yeah.
And then let me one last question.
I'll try to answer fast.
Peter, do you want to come?
The patterns are static, so I would assume you would have to time average the deposit of salinity on the surface and see if that looks like the surface of the lake.
Yeah.
And if they're moving, I'm wondering whether it would be an average and not see this pattern.
So no, we have done the average and we see clearly the patterns. There's also something else that we would like to add into the modeling, which is the feedback from the crust onto the evaporation rate. And that would make the pattern, I'm imagining, static because it would break the translation invariance of the systems. There are things like that.
Okay.
Okay, well let's thank Cedric again.